Welcome back, everyone. We're here for database modules 7.3 through 8.1, and in the next videos we are going to have a lot of good information coming at us and a lot of kind of complex stuff. So I wanted to take this opportunity to have a quick review before we talk about attribute closure and then move on to functional dependencies and normalization. So just as a reminder, our functional dependencies specify relationships between attributes in a relation. And some of our functional dependencies are semantically obvious, meaning they were described to us in the business case. And then some of our functional dependencies are inferred using Armstrong's axioms to create new functional dependencies based on the functional dependencies that were described to us by the business. And we can represent functional dependencies using what we call a dependency diagram, where we have our relation schema and then have some arrows pointing between the attributes. In this case, describing these functional dependencies as store functionally determining location, square feet, and manager, store and product together functionally determining quantity, product functionally determining price, and quantity functionally determining discount. We say an attribute in a relation schema functionally determines another attribute if for a given value of that attribute there is a single specific value of the attribute that it functionally determines. So we write this as one attribute and then an arrow pointing to another attribute. The attribute on the left-hand side of the arrow is called the determinant, and the attribute on the right-hand side of the arrow is called the dependent. So in this case, we say A functionally determines B, or B is functionally determined by A, or the determinant functionally determines the dependent, or the dependent is functionally determined by the determinant. Now, functional dependencies are a critical part of databases, and they describe how our business uses the data. So functional dependencies are in and of themselves a good thing and a necessary thing for our databases. However, some functional dependencies are what we call undesirable. And an undesirable functional dependency is one where the determinant is not a candidate key of the relation. And I said this twice in the last video, and I'm going to say it twice again because it's so important. Our problematic or undesirable functional dependencies are ones where the determinant is not a candidate key in the relation. And this is what causes data redundancy and modification anomalies. So it's important that all of our determinants be candidate keys in the relation. And in the next couple of videos, we're going to see how we can identify good candidate keys of our relation, and then when we find undesirable functional dependencies, how we remove or how we move those attributes and functional dependencies into other relations to resolve these data redundancy problems. And recall, when we say data redundancy, we don't just mean values that are repeated, because sometimes repetition of values is telling us something new with every repetition of that value. But data redundancy is when the repetition does not add any new meaning to our understanding of the data. And this leads to modification anomalies, which we saw in the previous set of videos, the insert anomaly, the delete anomaly, and the update anomaly. And we are going to resolve these problems with normalization, and that's going to be the focus of this series of videos. We interact with functional dependencies using Armstrong's axioms and the inference rules that are built on Armstrong's axioms. So there are three axioms: reflexivity, which says if y is a subset of x, then x functionally determines y. And we refer to these as trivial dependencies because they don't really tell us anything new and they are impossible to not satisfy. So basically this says if I know your PeopleSoft ID, your first name, and your last name, I could use that information to determine what your PeopleSoft ID is. or what your first name is, or what your last name is. A set functionally determines any subset of itself. Okay? This also means that an attribute functionally determines itself. If I know your phone number, I could use that to figure out what your phone number is, right? Pretty obvious. That's reflexivity. Augmentation allows us to add an attribute to the determinant, and that set of attributes will still determine any dependent that the determinant alone was able to functionally determine. So if your PeopleSoft ID functionally determines your name, then it's also true that your PeopleSoft ID and your shoe size could be used to functionally determine your name. So we can add something to the determinant, or we can add the same thing to the determinant and the dependent. So if your PeopleSoft ID functionally determines your first name, your PeopleSoft ID and your phone number could determine your first name and your phone number together. And then our final axiom, transitivity, uses two functional dependencies, and if we have an attribute that bridges these functional dependencies, in this case X functionally determines Y and Y functionally determines Z, then it's also true that X functionally determines Z. We also have 4 inference rules. Union says that if a determinant determines two dependents independently, then it also determines those dependents together. So if X functionally determines Y and X functionally determines Z, then it's also true that X functionally determines YZ together. If your PeopleSoft ID determines your first name and your PeopleSoft ID determines your last name, then your PeopleSoft ID determines your first name and your last name together. Decomposition is just the opposite of this. If a determinant determines two attributes together, then it also determines those two attributes separately. If your PeopleSoft ID determines your first and last name together, then the PeopleSoft ID could also be used to determine your first name, and your PeopleSoft ID could be used to determine your last name. Our composition rule says that if we have two functional dependencies, even if there's no overlapping attributes, we can combine the determinants and combine the dependents. So if A functionally determines B and C functionally determines D, then it is also true that AC functionally determines BD. And then finally, my favorite one to say and to do, pseudotransitivity, says that if we have a set of attributes as our determinant, and we have some other attribute that can functionally determine some subset of that set, then we can create a new functional dependency. So if X determines Y and YW functionally determines Z, then it's also true that XW functionally determines Z. Because if X determines Y, well, anywhere we have a Y, we could put an X in its place. Because if we know the value of X, we know the value of Y. So if X determines Y and YW determines Z, then it's also true that XW would determine Z. The final thing we talked about in the last series of videos is the cover and closure of our set of functional dependencies, which we refer to as F. The closure of F is all possible functional dependencies that we could infer based on the semantically obvious functional dependencies in F. So this is going to be a large set of functional dependencies. The minimal cover of F is a smaller set of functional dependencies that is equivalent to the set of semantically obvious functional dependencies. And we infer both the closure and the minimal cover of F using Armstrong's axioms. And there's one step further we need to go with this idea of closure, which is not just the closure of F, but the closure of each individual attribute. So this is similar to the closure of F, but we're looking at single attributes. We want to find all attributes that can be functionally determined by each attribute or each set of attributes in our relation. We express this by using by putting a plus sign next to the attribute, and we read it as the closure of that attribute under F. Okay? So if we were finding the closure of your PeopleSoft ID, we would say the closure of PeopleSoft ID under F. To give an example here, imagine we have this relation with 7 attributes, A, B, C, D, E, G, H, and the only reason we're skipping F is because we use the letter F to describe the set of functional dependencies in the relation, so no big deal there. And we have these 3 functional dependencies. B determines GH, A determines B, and C determines D. So we want to find the closure of attribute A. So first we know that A functionally determines B, and then through transitivity we can also say, well, if A determines B and B determines GH, then we know A functionally determines GH. And then because A determines B and A determines GH, we know A determines B, G, and H. And then through reflexivity, that A functionally determines A, we know that in the closure of A functionally determines A, B, G, and H. And I don't think there is anything else we can functionally determine because G and H are not determinants of anything else. So the closure of A is A, B, G, H. Since G and H don't determine anything else, the closure of B is going to be just BGH, and D doesn't functionally determine anything, so the closure of C is just CD. Now here's a question: would it be of any help to find the closure of AB? And the answer is no, not really, because A already functionally determines B and everything that B functionally determines, so this isn't going to add anything. However, since C functionally determines some attributes that are not in the closure of A, then it actually would be useful to find the closure of AC. So A and C together functionally determine A, B, C, D, G, and H. So this is the idea of attribute closure, and in the next set of videos we're going to see how we use the closure of attributes in order to derive candidate keys in a relation.